So picking up where we left off last time, in this video we'll be looking at some examples of polarization, what type of questions you can expect related to this certain subtopic. So before going on to that, I said that we would discuss some examples related to polarization. So something which is very common knowledge related to polarization is that sunglasses are also polarized. So what those polarized sunglasses do is that they completely block incoming light at certain angles, right? And that is how they provide eye protection against sunlight. So these are how you see polarization applying itself in sunglasses. You also see polarization finding its applications in the production as well as the viewing of 3D movies. So how those, how we perceive those 3D movies and how we perceive something to be 3D also is strongly dependent on the phenomena of polarization. And the third one, for which we'll actually be seeing a small video just to see how it finds its application in privacy screen protectors. This is like a very recent innovation, and how you use the idea of polarization to produce protectors for phones which provide some sort of a privacy or which provide some sort of privacy of the basis of polarization. And these are just the more interesting applications. It also finds its analysis in some chemical processes called spectroscopy, and it also is used in the stress analysis of certain types of materials. So something like this is what I was referring to. So here you can see that at certain angles, like this one, you can see the screen very clearly, but at other angles, when the phone is tilted, you do not see the screen at all, right? So this is to prevent somebody who's sitting beside you, for example, from having a little sneak peek at your phone. So this is how you have privacy, because the only way you'll actually be able to see the screen very clearly is if you're looking at this head on like this. So this is the idea of how polarization finds itself in different applications. Now let's go towards the different type of exam questions that we may have. So let's have a look at the first one. So you'll see that these questions are made by me because you do not have exactly the type of questions which are asked in your exams in a lot of other places. So this is the first one: vertically polarized light which is incident on a polarizing filter which has its transmission axis at 45 degrees to the vertical. Right, so let's also try to make the diagram as we go through the question. So this is the transmission axis which is at an angle of 45 degrees to the vertical. Right, remember in Malice's law, when I told you about the angle, it's always going to be the angle between the incoming light and the transmission axis. So right here we have the incident light, which is like this. Also let's have another ray of light on the other hand to show the exiting light. So the incoming light is vertically polarized, so it's like this, right? So it's totally up and down because we have vertically polarized light, and the transmission axis is at an angle like this, which is 45 degrees to the vertical. Given that the intensity of incident light is 100 watts per meter square, find the intensity after passing through the filter. So we know that after passing through the filter, the direction, basically the plane of light, will be determined by the transmission axis. So it's going to be like this at an angle of 45 degrees. So something like this, right? And now we need to find the intensity after it has passed through the filter. Now this is really easy because we're just starting out. I deliberately kept the example very easy. So we know that we have to find the angle between the incident intensity and the transmission axis. So here, as the light which was incoming was vertically polarized, so the angle between the vertically polarized light is going to be this and till the transmission axis, so it's going to be 45 degrees. So then I can just go ahead and use Malice's law. So I equals to I naught cos square of theta. In this case, I naught is 100 and cos 45, and don't forget the square. So this turns out to be, so cos 45 is root 2 by 2 and square of that is half, so 100 upon 2 is 50 watts per meter square. Now let's say the second part of the question asks you find, or let's say it says state other angles from the vertical where the intensity is the same as you calculated. Right, so what the question is basically asking is that even at different angles, when will the intensity still be equal to 50 watts per meter square? Right, so we need to find these angles. Now you'll only be able to do this part if you have a very clear idea of theta, which I have repeatedly stated as the angle between the transmission axis and the vertically and the incident intensity. So in this case, as you can see, the angle between them was 45 degrees, which caused the intensity to be 50. So now the question you really need to ask yourself is this, that where else will the angle between the vertically polarized intensity and the transmission axis be 45 degrees? So I can see that this is the line basically which will be drawn where the angle is going to be 45 degrees. So I can see this is one point, and as the transmission axis rotates further, so again you can see that the angle between the vertically polarized light and the transmission axis will be increasing. At this point it will become 90 degree again when, for example, it's at a position like this. But then afterwards, the vertically polarized light would have an angle like this. So this is the entire angle that the vertically polarized light has, right? It's vibrating up and down. So even if it goes to a position like this, remember that the angle will not be this, the angle will now be this one, right? Always remember that you have to deal with acute angles whenever talking about polarization. So you can see that right now this angle is pretty large, but as this transmission axis further rotates here, right, as we further rotate the filter, this angle can also become 45 degrees, right? So at that point, when this angle is 45, you would again have the intensity being equal to this, because the equation would have the same form exactly once again. Then as you can see, when the transmission axis would rotate further towards a point like this, again this angle between the incident light and the transmission axis would again be 45 degrees. So again you would have the same intensity, and as it's rotating further and further and further, then again at a position like this, it would again make the same angle of 45 degrees. So the first one was this 45 degrees, the second one is going to be this thing. So if this is 45, so this would be 180 minus 45. So the first angle would be, so angles, the first one would be 180 minus 45, right? The second one would be, so 180 plus this 45, because we are asked the angles from the vertical. So this one is going to be 180 plus 45. And the third one, which is this entire angle, right? So this one would be what? So if this is 45 and this entire thing would be 360, so 360 minus 45. So now we can give the other angles. So 180 minus 45 would be 135. 180 plus 45 would be 225. And 360 minus 45 would be 315 degrees. So basically at all of these clockwise angles from the vertical, you would have the same intensity of 50 watts per meter square. And if you focus on the graph in the last lesson, you know that this is very easily possible. Let's have a look at another one. So this question says horizontally polarized light of intensity 36 watts per meter square is incident on a certain polarizing filter, and then it exits the filter with intensity 9 watts per meter square. And we need to find the angle of the transmission axis. Actually, let's correct this slightly. So find the angle between the transmission axis and the incident intensity. Right, so let's have a look at this now. Because with the vertical, you actually don't know what angle there could be. So I rephrased this question, corrected this slightly, so you know exactly what to calculate now. So we can see that this is the polarizing filter. We do not know what is the transmission axis angle. This is actually what we need to find. So this is the incident intensity, and this is the intensity of the light which exits. And we know that the initially incident light was horizontally polarized, so it's along these directions like this. And then you have some light exiting with some intensity. So in this case, if we need to find the angle, so this is not a problem, because Malice's law actually tells us the angle between the incident intensity and the transmission axis. So we really do not need to think about it as hard as we did in the previous part. So we can just go ahead and use the relationship. So I equals I naught cos squared theta. So I naught was 36 and this was 9, the intensity after passing through the filter. So cos squared theta is what we need to find. So cos squared theta is 9 upon 36, which is basically a quarter, and cos theta strictly speaking should be plus or a minus half. But what you'll see is that in this one we really don't care about the positive or negative, because the cos of a positive angle or a negative angle is still positive, right? So this is what we are just concerned with. We can just ignore the negative sign for now. So theta would just be cos inverse of half, which is 60 degrees, right? So the angle between the transmission axis and the intensity and the incident intensity is 60 degrees. But again, if I have to label the possible positions, know that I cannot just single out any one position. So if this is horizontally polarized, so one angle could be something like this, so that the angle between here and this is 60, or like this, so that this angle is 60, or like this, so that this angle is 60, and similarly like so that this angle is 60. So this is why I actually changed the question, because I just realized that this problem could also arise. So remember that there could be multiple positions for the transmission axis at which the at which the intensity which is exiting is a certain value.